Hello everyone, welcome back to StudyOnion, and today we're going to be talking about gravitation or gravity and how that is associated with Kepler's laws from last week. So, let's get started. So let's talk about Newton's laws of universal gravitation. This basically states that every body in the universe attracts every other body with a force which is directly proportional to the mass, so increases as mass increases, and inversely proportional to the distance between the two objects. So the force decreases as the distance increases. And therefore, we can assume that gravity is responsible for things like maintaining stable orbits and maintaining the motion of stars around galaxies and much, much, much more. So now let's have a little look at the inverse square nature of this law. So what the inverse square nature of the law is basically saying is that the intensity of the force is proportional inversely to the distance squared. So if, for example, the comet pictured here is 20 times further away from the sun at aphelion than perihelion, it means that when the comet passes perihelion, the force of gravity on the comet is 400 times greater than the force at aphelion. So let's have a little look at Newton's thought experiment. So Newton's Cannonball was a thought experiment devised by Isaac Newton. He hypothesized that the force of gravity was universal and that it was the key force in determining planetary motion. For this thought experiment, Newton basically visualized a cannon on the top of a tall mountain where there is no air. So he thought that if there was no gravity or air resistance, the cannonball should follow in a straight line away from the Earth in the direction that it was fired. Now, assuming that gravity does exist, A and B, depicted here on these slides, show what would happen if the object was launched into orbit with a low horizontal velocity. If it was launched with a velocity of 0, it would go straight down through the middle of the Earth. And if it was launched with a velocity of around 6,000 meters per second, then it would follow a trajectory which meant that it would end up crashing onto the Earth. If the cannonball had fired at the correct velocity, it would launch into an orbit around the Earth, and here that it would be a speed of 7,300 meters per second. And finally here, for D and E, this shows what would happen if the horizontal velocity is too high. So if there was a speed of 8,000 meters per second, it wouldn't be able to have a stable orbit. And the same applies for E, which is launched at a speed of 11,200. It would form a hyperbola and essentially leave the vicinity of the Earth. Okay, so let me just quickly mention a phenomenon called gravitational lensing. So you don't need to know too much about this, but it's really important that you learn this definition word for word. If they ask you to explain it, write this down and this should give you all of the marks. So gravitational lensing is basically when astronomers observe multiple images of distant galaxies due to the gravitational bending of light as it passes an invisible massive object such as a black hole. And you can see here on the right what that would look like for someone that is looking at those galaxies. So let's have a look at a worked example. So the first thing you do when you look at a question like this is to highlight some of the key words. So here, if it was me, I would be highlighting perihelion, aphelion, the values, and then the word ratio. These are all important because they have a factor when you are looking at how to approach the question. So once you've highlighted the keywords and you've understood the question, the next thing to do here would be to calculate the individual values of the force on the comet at perihelion and then at aphelion. So the formula for the intensity of the force is that intensity is proportional to 1 over distance squared. So if we sub in the values, we have 1 divided by 0.85 squared, and this is equal to approximately 1.34083. If we repeat the same process for the value of the force at aphelion, we see that there's going to be 1 divided. So if you, like the question asked, divide the value of the sun's force at perihelion divided by the force at aphelion, you get these numbers: 1.384083 and so on, divided by 0.03844. And this gives you an approximate value of 39.6433. And if you were giving this as an answer, you would give it as 39.6 to 1 decimal place, approximately. Now, you may be wondering, why are we able to replace my proportionality sign for an equal sign here? So the reason for this is because you're able to introduce a constant into the equation in order to do this, but obviously here I've ignored the constant, and the reason for doing this is because the constant will cancel each other out when you are dividing them, because you divide k by k, and that is equal to 1, therefore you don't have to factor it into the equation. If you wanted to, you could include it in the equation as just k, and that would work, and you would end up cancelling it out, but there is no requirement to do so. Alright, so to summarise, every object in the universe attracts every other body with a force which is directly proportional to the mass and inversely proportional to the distance between the two objects. The inverse square nature of Newton's laws means that the force's intensity is directly proportional to 1 over distance squared, and this can be used when doing calculations. Newton's thought experiment using a cannonball was used to hypothesize that the force of gravity was universal and that it was the key force for the planetary motion. It showcased that if an object is launched with too low a horizontal velocity, it will be unable to enter into a stable orbit, and the same is true for when it is launched at too high of a horizontal velocity. It is only when it is launched at the correct velocity will it be able to enter into a stable orbit. And finally, I just want to cover the definition of gravitational lensing. Gravitational lensing is when astronomers observe multiple images of distant galaxies due to the gravitational bending of light as it passes an invisible massive object such as a black hole. Hopefully you enjoyed that video, and I'll see you again next week with a new video beginning the telescopic astronomy part of the course. But for now, bye!